Hello, and thank you for joining us. I am Dawn Cullum, the Senior Training Coordinator for Certara University. For today's Certara software series, Ronette Gehring from Utrecht University will present on incorporating time variable clearance in a population pharmacokinetic model, an example from veterinary medicine. In most pharmacokinetic models, clearance is considered a parameter that is constant for the duration of the study. Disease progression, however, can cause the clearance to change over time. In this webinar, we will examine a case of that word, antimicrobial therapy for APEC and chickens to demonstrate how clearance can be incorporated into a population pharmacokinetic model as time-dependent variables. I don't care how many times I read this, there's always I skip over something, so I apologize for that. If you have questions, we ask that you put them in the Q&A section at the bottom of your screen. Ronette will have some time at the end of her presentation to go over them. Also, if you could make sure that you are muted, I would really appreciate it. Ronette, I'm going to turn it over to you now.
Thanks so much, Dawn. And thank you very much again for giving me this opportunity once again to reach out to our community of veterinary pharmacokineticists and pharmacometricians with an example which I at least think is very interesting, and I hope you guys will too. So what I'm going to address today is something that sometimes we don't really want to admit to, but what sometimes happens even though we may have the best intentions in how we plan our studies and execute our studies, is that sometimes we just influence the results through some experimental artifact that we don't necessarily expect when we're planning the study. And I hopefully will also, with this presentation, show you the power of modeling and how it can help, help analyze the data and explore ideas and actually make sense of what we're seeing, which can sometimes be very confusing when you collect data from a study where you simply can't always control everything that happens. And that's often something that happens in veterinary medicine when we're working with animals, and we're particularly also working with animals in large groups. So time variable clearance is what I'm going to be talking about. I need to upfront acknowledge some people who really helped, and this analysis and this project is ongoing. So first of all, Janine Wichel, who is my PhD student and whose project this is, so she came up with the idea and also executed it, and it was not an easy study to execute. Also, Stephanie Horst, who is one of our trainees, who helped a lot in cleaning up the data, sifting through the data, making sure that the data that we are using is in the right format and is cleaned of all potential mistakes. And then Bernd Wendt, who has been a great partner, and this has definitely been a team modeling effort. So I'm going to start off with the data, telling you why we did the study, where it comes from, what was the study design, and then looking at some initial results, so just plots of the data to show you what the data looks like. Then moving on to the modeling, talk about the base model that we thought, oh, this will fit the data nicely. A bit of a spoiler alert, it didn't, so we needed to go on to refine the model. Particularly, the key there was to think about incorporating time varying clearance. And then once we had the model, how we're now using it to explore certain potential relationships and potential explanations. And then because this is an ongoing project, talk about some next steps, like, for instance, looking at additional covariates and further refinement of that varying clearance. So just a little bit of background. Colibacillosis in poultry, an infection caused by a pathogenic strain of Escherichia coli or avian pathogenic E. coli. So that's where APEC comes from. It can cause either local or systemic infections, and these systemic infections can manifest in a diverse number of ways, including acute septicemia, subacute pericarditis, asacculitis, salpingitis, peritonitis, and cellulitis. As you can see, it can be a pretty serious disease, and it is a major cause of morbidity, mortality, and economic loss in poultry worldwide. One of the registered treatments for this infection is doxycycline, and in the Netherlands, at least, not in all countries, but in the Netherlands, it is listed as the first choice, which means that unless you can demonstrate that doxycycline will not be effective, that is the treatment that you should go to first. But of course, that also means that we need to optimize this treatment to ensure efficacy, and because this is mostly poultry for human consumption, to avoid any potential residues. So our goals were to describe the pharmacokinetics of doxycycline in broiler chickens when administered under field conditions. So that would be within a flock, and also a diseased flock. So we also wanted to look at what could potential covariates or what would be the effects of different covariates on overall exposure, and particularly challenge. And with challenge, we may mean challenged with the bacteria to cause disease. And also our other question was bedding, whether bedding, because these animals are on the floor, these chickens are on the floor, could potentially lead to re-exposure, and what that effect would be. I'm not going to talk about the bedding effect in this talk. Maybe that will be a talk for next year once we've looked at all these different covariates in more depth. What I'm going to talk about today is I'm going to focus in on the individually treated animals, because we had two legs to the study. One, we had individually treated animals so that we knew exactly what the dose was that was administered orally to these animals. And then we had another leg where we had animals treated as a group through the drinking water, which of course brings with it an additional unknown in terms of what the actual exposure was. But first, in the model development, we focused on the individually treated animals. And just some more details about the study. So we brought in 28-day-old broilers, or we were focusing on 28-day-old broilers. They were divided into a group that was challenged and a group that was unchallenged, or a control non-healthy group. But those birds that were challenged with 10 to the power of 7 colony-forming units per bird of E. coli. The strain was 507. And then we went on to treat all birds, so the challenged and the unchallenged, orally with 25 milligrams doxycycline hyclate per kilogram body weight per day for 5 consecutive days. And that was either a bolus dose directly into the crop or by drinking water. And the blood sample, then we collected blood samples from the cephalic vein, and these were then analyzed for doxycycline concentrations using LC-MS. And very importantly, also, we monitored water intake throughout the study. On the right-hand side, you can see, once again, a overview of the study. So quite a complex study, I'm sure you can appreciate. And once again, we are focusing on the individually treated animals. So here we have an initial spaghetti plot. So first step, obviously, once you get your data in, exciting, let's see what the data look like. And we plot them as and the easiest way to look at what is going on, or the first step to look at what's going on, is to look at to create a spaghetti plot. And here we have in purple the sick birds, so the birds who were challenged with the E. coli, and healthy birds in orange. And immediately we see that, is particularly in the earlier times, the sick birds seem to have higher concentrations than the healthy birds. It seems to come together at the later time points, although on average, the sick birds still seem to have slightly higher concentrations, which can be interpreted as higher exposure. You'll also see for the sick birds that for many of the individuals, the time concentration curves are incomplete, and that is because they got quite sick with the challenge, and many of them fell out and died or needed to be euthanized earlier than was, so they couldn't complete the entire study. And if we look at the data, and it's fairly sparse data, so we looked at what would be the best model to fit. And of course, the law of parsimony tells us that we should go for the model that is the simplest and would likely be a good fit to the data. So we started off thinking, or started off our modeling with fitting a one-compartment model, obviously with extravascular administration, because this was oral administration as a bolus, with first-order absorption and first-order elimination. And here I have the initial or the diagnostic plots, so the predicted versus observed for that initial one-compartment model. On the left-hand side for the entire range of concentrations, and on the right-hand side, focusing in on the lower concentrations. And hopefully the modelers amongst you will see that this is not very great, particularly at the lower concentrations. We are very much over-predicting, so there is bias in our predictions. So what is happening here? Well, this would be the time to then go to and look at the individual concentration time curves and see how is the model doing in terms of a fit. And here we are looking at the individual models and the individual fit. And as you can see, the problem that's probably leading to that bias is in the beginning. And these are then particularly in the individuals that are healthy, we see that we have a problem to fit with a uniform model to all the data points, and in trying to fit an average good enough model, the same model to all the data points so that we get a good fit. The problem, it's pretty problematic for the initial time points.
Ronette, I'm sorry, we have had someone to ask if you could use a pointer.
Oh, okay. Yes, I can use a pointer. Let me have a look, make sure. Make sure I can find. There you go. Do you?
We can see that, yes.
Can you see this? Okay, yeah. So here we see, for example, if we take this first individual, here we can see the initial time points, over prediction with the model, and many time points below that prediction. Here we have the same, here we have the same, here we have the same again. So this systematic over prediction, particularly of the lower concentrations, seems to be a problem, particularly in the initial time points, but also because the program is trying to fit an average model or the same model to all the data points. We see that that systematically the model is missing the lower time points. And particularly because we had this difference in concentrations in the healthy animals initially, and then it could not be explained by accumulation, because doxycycline has quite a short half-life in chickens. We thought there's something different in the beginning that changes over time. And what we thought was, well, could it be that clearance is different? So we have animals that are pretty sick, and and are under circumstances where perhaps clearance is changing over time. So we thought to improve this model fit, which is really not very good, we will try two things. One is, can we code a model where variance changes over time, so it's not constant? And secondly, because these animals are getting pretty sick, should we maybe not add sickness as a covariate? And here you can see a comparison between the different models. And we see that when we go from the base model, which is just a one compartment model, first order absorption, first order elimination, when we go from that to adding this variance clearance, we see that, for instance, the Ikaike information criteria, there's a big difference, 120 points in difference. So we really gain a lot by including this variant clearance. If we then go and add sickness as a covariate, we have very little difference. And even for some measures of fit, like the Bayesian, the BIC, we even get a higher number. So we were really, really interested that variant clearance really seems to be what's happening here, and we got a nice, a much better fit. So some of you might ask, how did we actually do this? And this is where I reached out to Bent. Please help me. How can I code this? So you see here that we have clearance that has a starting clearance, so clearance 0, and then it gets adjusted. And how it gets adjusted is by a factor A, so we introduce two things. We introduce a factor A, and we introduce a parameter called T cut. And when time is less than T cut, then we see that clearance varies with time by a factor A. And then after T cut, then clearance stabilizes to a value which is A times T cut. So that's how we coded this into Phoenix, and we got much better fits. So here we see at the lower concentrations, we no longer have that systematic bias. Sorry about that. We no longer have that systematic bias, and we are managing to fit both the earlier time points and the later time points better, because we no longer have the program stuck with using only one clearance. And then we started, so this was initially a modeling problem. How can we get this model to have a better fit? And we managed to do that. Then, as physiologists or as veterinarians, we stepped back and we thought, well, okay, fine, we got a better fit now. How can we explain this? And one of the things that I mentioned initially is one of the nice things about the study design is that we monitored water intake throughout the study. And here we can see water intake. And here the orange is, once again, the healthy animals. The purple is the animals that were challenged and got sick. Here the time 0 is not the beginning of challenge or the beginning of the pharmacokinetic study, but it was when these animals were brought in for acclimatization. So they came in healthy, young chickens, all of them in the same health status, but we see that at time 0 we have quite a high water intake. For those of you that are poultry experts amongst you, you'll know that a water intake above 300 is probably pretty high for these animals. 200 is maybe on what we would expect, but we can explain this probably that they came in slightly dehydrated because of transportation and handling. Then we see that between 0 and 168, it stabilizes round about that 200. So they're acclimatized, it's stabilized. And then those two parallel lines, the vertical parallel lines, that was when we did the infection, so the challenge, and then the pharmacokinetic study started. And what you see is a slight dip maybe around the infection challenge, the day of the infection. but then a compensation again, and then a very marked decrease in water consumption during the first day of the pharmacokinetic study, which then recovers in the healthy animals, or the animals that were not challenged. But then the animals that were challenged and got sick, we see that they hardly recover, or some of them recover, but much later. So there's definitely an influence on water intake. And that would possibly, particularly because we see that the clearance in the beginning of the study is lower than the clearance later on, it seems logical physiologically that that could influence clearance. And so we did another plot. And here you see the time starts at 144, because this is where we started with the challenge. And then at 168, this is where the pharmacokinetic study came in. Sorry, no, 144 is when we began with the pharmacokinetic study. And why would water consumption decrease during the first day of the pharmacokinetic study? Well, these animals were handled a lot for blood collection. So they were stressed, they didn't know what was happening, and they were didn't have time to drink as much, or when they were stressed, they didn't think of drinking that much. So we see the drop in water consumption and an associated drop in clearance, more so in the challenge in the sick animals so in the sick animals than in the healthy animals, but in both animals a drop in water consumption with a lag, but an associated decrease in clearance, which then later stabilizes, and it stabilizes at a lower level in the sick animals than in the healthy animals. Now, this is just a graphical association, so it's in support of what we think is happening. We want to explore including water intake into the model as a covariate, but at this stage it's not so easy because, and I'm sure you can appreciate that looking at the water consumption data, because there's a lot of variability. It is all over the place. Although there is a trend, particularly at the later times, there's a lot of variability. So that clouds everything and clouds it in terms of including it as a clear covariate. Another exploration we've done is to plot clearance versus water intake. And here we can see a trend that does seem related, particularly at the extremes. So very low water intake and higher water intake. There seems to be a relationship, something to explore further as well, and also a support of what with of the direction we're thinking in. And then we can also look at the covariate plots, and what we see here, which is interesting, is that disease does seem to also affect clearance, and we see that the clearance does stabilize seemingly at a lower level with the sick animals. However, we haven't been able to incorporate that into the model yet to an extent that it's a significant improvement in the fit, and also that the T-cut is significantly affected with the challenge. And that says to us that the clearance decreases faster in the challenged, so in the sick animals, which also makes sense because they drink less and they also don't recover. So you get a faster and a more severe effect on the clearance. Interestingly, volume of distribution is not affected by illness, so that is interesting to see. So we have our next steps planned out. This relationship between water intake and clearance is complex. There's a lot of variability. So can we in some way simplify the data so that we can get a clear relationship, perhaps look at cutoff values for hydrated or not, or dehydrated, and also how this model is now coded. We have a varying clearance up to a point, which is T-cut, after which it stabilizes, which gives a good fit, but is maybe not the best fit because clearance probably also recovers. And we need to think about how we can potentially incorporate that into the model. And then we need to look at including challenge as a covariate for clearance and T-cut as well, because there seems to be a clear influence. However, at this stage, because of the high variability, we have not yet managed to include it as a covariate that leads to a significantly better fit. So some take-homes, that when you look at your data, don't forget to consider the study and how that could have influenced your data. So we thought challenge sickness affects clearance, and it does seem to affect clearance, but also the fact that we were handling these animals a lot, that they were stressed, that they were not drinking as much, seemed to affect the pharmacokinetics and affect the data that we gathered. And luckily, we had that water intake data. Without the water intake data, we would not have known what's happening, and we would have just said, well, we can't get this model to fit. Try out different ideas in your model to improve the fit, and sometimes the modeling can help you come up with ideas. And that was definitely what happened in this case. But always then go and look and seek physiological explanations for what you see. And with that, I'd like to thank you for your time. And of course, if there are any questions, I'd be happy to try and answer them.
Great. Well, we do have one question, and actually, I'm sorry, we have several popping up now. But if you have a question, please remember to put it in the Q&A. Ronette, someone was asking, could you please explain what challenge equals 0 and challenge equal 1?
Yes. So, good question. So these animals were challenged with E. coli to make them sick, and because within Phoenix, you need to code. You need to code the different potential covariates, and you have two options for covariates. The one is a categorical, and the other is continuous. And we then, so whether a chicken is sick or not sick, which means was it challenged with E. coli or not challenged with E. coli, we then coded as a binary 0, it was not challenged, so healthy; 1, it was challenged, so it would be sick.
If you were to repeat this study, would you do anything different?
I think that perhaps we could, knowing now that it seems like the study affects water intake, we need to think about how can we perhaps acclimatize, not just acclimatize the birds to their environment, but also to being handled, so that they are less stressed and surprised when the pharmacokinetic study, part of the study, comes along, and they're being handled 4 times a day, taken form 4 times a day for blood, blood collection. So that would definitely be something that I would consider going forward in any study in chickens now that I've seen that this happens.
Okay. This is a, go ahead.
Sorry, Dawn. Yeah.
This is a 2-part question. So the first question is, when we choose CL varying over time in the model, is there any indications in the exploratory data analysis, EDA, to take into consideration that CL changes over time in the model? How the modeler justifies that?
Yeah, very good question. So we did a step, and I didn't, because of time constraints, I didn't show that. But a step that we did before fitting the compartment, well, once we'd fitted the one compartmental model and saw that this is not going to work, we took a step back and we did a non-compartmental analysis, and we did we looked at the area under the curves for the different time periods, And then we could calculate a clearance during the different, so with non-compartmental analysis, we saw that we're probably dealing with a different clearance in that first 24 hours compared to the other time points. So taking a step back and doing a non-compartmental analysis and looking at your data descriptively is a good first step to justify, okay, let's try this in our compartmental model.
Second part of the question, what is biological explanation for changing CL over time?
At this stage, how I am explaining it and how I think we're as a group explaining it is that decrease in water intake leads to dehydration, which leads to a decrease in perfusion of the excretory organs, which affects clearance. So at this stage, but if there are any people out there that are experts in chicken physiology, I'd be your suggestions would be most welcome.
Would you consider feed intake important?
We did not consider feed intake. We also didn't measure feed intake. Well, yeah, I don't think we measured feed intake. Well, the study was looking at, I've shown you the data for the bolus administration, but we were also looking at water intake. So water intake to us was important, but it was important because that also leads to the dose, the actual dose that each individual chicken gets. So we were focused on water intake. I think that feed intake, a decrease in feed intake is a general indicator of stress or illness, which can be an indicator of general, physiological changes. So it could be a clue. I think at this stage that it would probably be less directly related to any change in the pharmacokinetic parameters, particularly clearance. But that would be for this case. In other cases, obviously, absorption could be affected by feed intake, importantly, and also excretion. So depending on your drug, depending on under the circumstances, I think it's always important to consider all these factors.
I think we've pretty much answered this next question with that, but we can tag on a little bit more. The question is, apart from water intake and challenge, can you think of any alternative covariance?
I think that, we do have an alternative covariate or additional covariate that we are going to be considering as we go forward, and that is whether these animals are kept on bedding or not. I think you could also think of activity. Just general activity would be another one. You have to think of covariates that you can measure in these circumstances, because these are chickens kept in large flocks, and we've already seen what the effect is of handling on water intake, so you don't want to disturb them even more by measuring other things. I would think maybe, but we are limited in the volume of blood that we can collect from these animals. But we could have maybe thought of, now in hindsight, maybe thought of hematocrit, for instance, or some measure of hydration, if we were taking the blood anyway. But the problem is that we didn't have very large blood sample at that, and it's never really possible to take large blood samples in chickens.
Is there a correlation between clearance at initial time with that of later time points?
Oh, yeah, that's something to think about. So you mean within chicken, that within chicken, a chicken that started off with a higher clearance also stabilizes later at a relatively lower clearance, but it would be higher than the clearance that of a chicken that started off at a lower clearance? That's a very good question, and something that I think we're going to go and explore. I think we could potentially look at, if we look at this graph, I think that there does seem to be a relationship between, individuals starting off with a higher clearance seem to stabilize at a higher, later at a higher clearance than others with a lower clearance. So yes, there does seem to be. Good question. Thanks for that.
What is your opinion about exploring a variable related with the functionality of the excretion organ as a covariant, as a more direct covariant, a representative covariant of changes that affect the clearance?
Okay. If I read, I think maybe that's important to clarify that in this model, so the varying clearance is not a covariate; it's part of the structure of the model. So we're so we began with a structural model where clearance was fixed, which is what is typical for pharmacokinetic models, and within that base model, we explored different covariates, or the covariates like challenge or no challenge, and also bedding, and we did not get a better fit. And that's where we thought, where we realized we need to look at the structure of the model. Another thing is that covariates versus the structure of the model, if you have systematic bias like we had, that is more likely to be a problem with the structure of your model than with a covariate. A covariate addresses variability and can zoom in and close and decrease the variability in your predictions versus measurements. But systematic bias is more about the structure of your model. And this is an example where, so the varying clearance is part of the structure of the model. It's not a covariate.
Did you calculate AUC at different doses to capture challenging CL over time?
Yes. No, not different doses, at different times. So at different time points, we calculated the AUC, and that's what gave us a clue that clearance was different. This study, we only used one dose. That was 25 milligrams per kilogram. So we do not. The study was not designed to look at different doses.
What is the advantage of this complex model over a similar descriptive NCA?
Yeah, so because I hope that that this kind of helps, this presentation also helps kind of illustrate this, how with an NCA you see what is, right? So this is the area under the curve, these are the clearances are different, so you see what you see, but by trying different ways of fitting a model to the data, you are then also actually writing a story, right? Your code is a story that you're writing, albeit in mathematical language. And by trying to get this story to fit to your data, you are then coming up with potential explanations for what's happening, and then that you can then go and explore further. So that to me was the eye-opener with this project.
We do have a question. I'm not sure we're going to be able to do this right now, but they want you to show how to run the fitting in Phoenix.
Oh, yeah. I think that would probably be a time of something for a different kind of webinar, which is more technical. And I think that there are also through Certara University and also through the Certara YouTube channel, various videos that you can watch where this is shown, how to go about running Phoenix how to import your data, how to select your model, and how to run the fitting, and then after that to evaluate your fit as well. So I think it doesn't really fit within the time constraints that we have, and also the goal of this webinar. But there certainly are Certara resources for that.
And you can reach out to us at any point, and we will do our best to help you. So Ronette, thank you very much for your time. And again, everyone, we thank you for joining us today. Our final webinar of the series is scheduled for October the 19th, when a team consisting of Stefan Smit, Dane Chung, and Mohammed Aslam from the University of Florida will be presenting on model-informed drug development applications in Phoenix, selected maternal and pediatric health applications. With increased regulatory burden and high expectation from prescribers and patients, it is no longer cost nor time effective to tackle all open questions experimentally. And as a result, an increasing number of decisions is informed by modeling and simulation approaches, which integrate all available knowledge in a quantitative and objective manner. During this webinar, they will provide a brief overview of the current state of modeling and simulation in drug development and regulatory evaluations, followed by 2 case examples. The first case example will discuss the use of a time-to-event analysis in Phoenix, which is aimed at identifying optimal dual therapy for patient deductus oratorius closure in preterm neonates. The second case example will be subject to a model-based meta-analysis in Phoenix, which aimed at characterizing dose-response relationships of selected combined oral hormonal contraceptives using Pearl Index and ovulation rate as primary and secondary efficacy endpoints. We look forward to having you join us on October the 19th. And we have a message that says, thank you. This has been a very interesting seminar, and we thank you for those wonderful comments too.
Thank you very much. Thanks for your attention.
Have a wonderful day.
Bye.